Hello. Okay, so I'll be covering. Let me just. I think there'll be some background noise. You'll have to bear with that. I'll be covering slides 1 to 6, provided by Satish sir for the CS batch. So that's the primary reference. I'll just go through all the topics that were covered in each of the PPTs. All the content of the slides is not present in what I've written. So whatever you're seeing on your screen, it's either the topic headings. Some of the topics I've covered, but not all. So you will still have to skim through all the theory that is there in the slides. I mean, it's not like every word is important. Most of it is very much bloated, repeated, and all sorts of things. So you could just skim through the theory and focus on the topics that are there in this document that you're looking at. So in the first PPT, there is some theory about what is AI and all those things. There is also something about what is a Turing test. So you can read, you will find them in the slides. Then there's something called an agent. So agent, environment, and all those things. So what is an agent? So let's say you have an environment and then you have an agent. An agent will be able to perceive the environment through using its sensors. So an agent will have sensors. It will be perceiving the environment by using its sensors, and the thing it's sensing is called percepts. So it makes sense of the world around it, of the environment around it, using its sensors. And I think agents have something called actors. I don't know if this is or actuators. I think they have something called the actuators, which will actors or actuate. I'm writing both of them. I think one of them is right. Which will let the agent perform some kind of an action, which will in turn affect the environment. And this keeps going on. So all this theory is there in PPT 1. Agents, environments, actions, all those sorts of things. And then what is a rational agent? An agent that displays intelligent behavior. Now what is intelligent behavior? All those sorts of all the theory related to that is there in PPT 1. And then you have something called PEAS. I think it's a sort of a framework that an agent is supposed to follow or something. You have the environment, you have an actuator, you have sensors, and we can rate its actions. So if it performs in a certain way, we can give it a higher performance measure. Maybe that makes it more rational and things like that. So all the theory is there in PPT 1. There are different kinds of, this is also there in PPT 1. There are different kinds of agent types. Simple reflexes, basically if you now again here you're sensing that the human is hungry. So if the agent senses that the human is hungry, so it directly performs an action called get food. So it gets food for the human being. You have another agent which stores a state. So instead of simply sensing, it has some memory of some sorts. So what it will do is, once it senses that a human is hungry, it will also check if the food is ready or not. So it has some memory. some state. It remembers something about the environment. In this environment, what do we have? We have food. We have human being. We have food. It checks if the food is ready or not, or it remembers. More like it remembers instead of checking. If it remembers that the food is ready or not, then it will act accordingly. If the food is not ready, then it will prepare food. So here the thing is, it is acting not only based on its senses, like reflex senses, they could be used interchangeably. That is there. State means it remembers something. Now, if to the same thing, if you add a goal means you give it a task. Like you could say it to the agent, complete everything, like do this, perform this task within 30 minutes, or you could give it any other thing. Like I mean, I couldn't come up with a better example, but you give it a goal, you give it an end goal. You're supposed to do something. Uh, let's say, I don't know. Just come up with some examples. So the third kind of an agent is, first kind of an agent, it simply reacts to something that happens in an environment. The second kind of an agent is, it does the same thing, but then it also has some kind of a memory. It remembers the state of a certain something. In this case, it is the state of the food. Is it ready or not? A third kind of an agent is, you give it a sort of a goal. What sort of a goal? In this example, you can ask the agent to finish everything within 30 minutes. That's a goal. It has to abide by that goal. Because if it doesn't, then it fails, and that's bad for the agent. The fourth kind is utility based. Utility, you could think of it as happiness or desirability, anything of that sort. Utility, we're trying to maximize utility here. So in this example, we could talk about something like taste. We would like to maximize the taste of the food so that the human is so that the human becomes more happy. So you want to maximize happiness. So that is utility. That's it. So you have four kinds of agents. That was PPT 1. There was nothing much, but there is some theory. You could go through all of that. AI Winter and all that. That was there. In PPT 1.2, the first thing that comes up is now properties of environments. We've seen what kinds of agents are there. Now we look at what kinds of properties are there. Properties of environments. So accessible, observable. Now it's all simple English. So you will be able to understand. Complete access to the environment. If an agent is able to get every single detail of the every single information, every single piece of information from the environment, then the environment is accessible or observable. If it is unable to get it, then it's not accessible. For example, let's say I'm an agent. I do not know, I do not have complete access to the Endsem paper making thing. So that sort of an environment is inaccessible for an agent like me. So if the student, let's say there is some agent that is within the environment, then they will be able to access the Endsem papers. For example, professors. So let's say those are agents. For them, they can easily access all the Endsem papers because they are the ones who are making it. Something like that. You can think of anything like that. Deterministic. Next state depends on current state and actions. So basically, if you do something now, then your actions will determine what the next state is going to be. So for example, if I hold an apple and leave it mid-air, it's going to fall down. So you could determine that yes, after some time it's just going to hit the ground and then remain on the ground. So that's deterministic. But there's something called subjective. Okay, wait, before going to subjective determinism, non-deterministic means whatever you do, you will not be able to predict what is going to be the next state. I think state is easy to understand. So, for example, let's say I have a coin and then I flip it. The coin could possibly only, not could possibly, the coin will only have two states. It'll either be heads or tails, right? The final state of a coin is either heads or tails. Ignoring the possibility that the coin is probably thick and it's going to be in between heads or tails. Ignoring that possibility. So if you are able to determine, if your actions and the current state are going to determine what the next state is going to be, the environment is going to be deterministic. About subjective determinism, it's just that as time passes or whatever, there will be too many variables to think about, and then you lose track of all the information, because of which you will not be able to determine what the next state is going to be like. For example, look at weather. See, weather seems like it's non-deterministic. You will not be able to accurately, with 100%, this thing be able to predict what is going to be tomorrow's weather. You will still have some. It's all predictions. No one's going to say with 100% accuracy that tomorrow it's going to rain, tomorrow there'll be thunderstorms. Is this an example of non-determinism? No, it is an example of subjective determinism, because it's just that you can't keep track of every single atom and molecule in the atmosphere. If you can do that, then you can determine what the weather is going to be like tomorrow, but you can't do that. So that becomes subjective determinism. So it feels like it's non-deterministic, but it's not non-deterministic. It's actually subjectively deterministic. Episodic means, let's say you have an agent that simply scans the environment, assesses something, and then it's like, okay, let me perform a certain action. And after it performs its action, it's going to forget about everything. Again, scan the environment, analyze whatever it wants to, and then perform an action. So it's like the current actions. It's like one episode doesn't affect the other. It just keeps doing its work. For example, let's say an agent that is picking boxes or arranging boxes on a shelf. This was the example in the slide. What does it do? It finds a box on the ground, it lifts it up, puts it on the shelf, and then it resets. It will again start looking for boxes on the ground, picks it up, puts it on the shelf, and then it goes on. The agent behaves that way. So the environment is such that there's nothing much to do. You pick a box. So what is there in the environment? You have a shelf and you have boxes on the ground. But how is it a property of an environment? It looks like how an agent is doing its task. But anyways, this was given. Essentially, the current one episode doesn't affect the other episode. If you get that point, then it's fine. It's not like it's very important. Static environment is basically when an agent is analyzing the environment, or when it's performing an action, it's not supposed to change. The environment is only supposed to change after the agent completes performing its action. For example, if an agent is playing chess, it's not like let's say black made its move and white is thinking about its move. It's not like black is going to make its second move. No, it's not going to happen. The environment is going to stay as it is. No changes will be made on the chessboard unless the white player makes their move. So it's a static environment. But if you think about weather, it's not like that. If you look at the sky above, just because you're analyzing, it doesn't mean the clouds are going to stop. They will keep moving. So you could think of weather as a dynamic environment, not a static environment. Discrete is basically you can count all possible states of the environment. For example, coin flipping come under this? I'm not sure, because whatever you do, it will either be heads or tails. There are only two possible states of the entire coin flipping environment. So you could say it is a discrete environment. And I told you, percepts are those things that an agent perceives from the environment actions, the action that an agent does to affect the environment, to change the state of an environment. Fine, those were the different properties of environments. Uncertainty, you know what uncertainty is. If you do not have complete access to a certain, if you do not have complete access to the environment, it's basically uncertain. You can't predict. For example, you cannot certainly predict what questions are going to come in AI exam. So it's uncertain because you don't have access. But on the other hand, if you were a professor, you would have had access. You would know what questions were coming in the exam or whatever. And non-determinism. If non-determinism, you've just seen, if whatever you do, you won't be able to predict what the next state of the environment is going to be. So that's non-determinism. And if you have non-determinism, you cannot be certain as to what the next state is going to be by definition. So uncertainty, that is also very easy. Learning agents. Now there is something called an agent, there's something called a rational agent. Now there's something called a learning agent. Learning agent will so agent, rational agent, learning agent. Basically, it learns from its mistakes and then improves itself. That's it. That's a learning agent. That was PPT 1.2. You can go through the theory. PPT 2. There's something about search. What is search? In simple words, it's basically a sequence of steps that moves towards a solution. There's more theory you can read in the slides. Problem space hypothesis. There's something about problem space hypothesis. There were like 2 sentences in the PPT. It's like if you have any problem, you can convert it to symbols of some sorts. So you can represent a problem in terms of symbols and variables, and that thing will be called problem space. And solving that problem is essentially traversing through that entire problem space until you find the solution. Like in nice words, in formal words, it's explained in the slides. What is the problem space hypothesis? Essentially, you have a problem, you represent it in terms of symbols and variables, and that will finally be called the problem space. You'll have to keep traversing through all possibilities until you find the solution. Problem solving agents. So agents that solve problems are problem solving agents. I mean, there'll be more theory in the slides, you can go through them. So search space. Yes, so search space is essentially all possible combinations. So let's say you have a problem and environment has states, right? So if you collect all those states, all possible states, and put it in a set, that will be called search space. So you'll have to keep searching through this entire search space to find your suitable solution. But how do you begin? You'll have a start state. So from your start state, you'll have to keep going to different states, possibly your neighboring states and its neighboring states, so on and so forth, until you find a goal state. But there's something called a goal test. Goal test is essentially a function that keeps checking if the current state is equal to the goal state or not. There are different ways of searching, which we will see now soon. So yes, that's what I was talking about. You convert the problem into symbols and variables, and that's how you will represent. That's how you're going to represent a problem on paper. Production rules. There's an example in the slides. What does it do? Production. Let me just see once. Basically, in production rules, you have the current state, and then you have a constraint of some sorts. Is it a constraint? No. It's not a constraint. You have the current state, and along with the current state, you have a condition that has been satisfied. And because this current state and a condition has been satisfied, because of these two things, you will move to a new state. It's like those transition functions. If you remember in TOC, for if you're on a, if you're in a certain state and then you get a certain letter as an input, you move to a new state. Similarly, if you're in a certain state and if a certain condition is satisfied, you move to a new state. So if you open the slides and look at the examples, all of this is given under production rules. I didn't write anything about it because I think it's not. I think nothing specific could be asked. It's just general knowledge. I think that's why I didn't write anything here. You could look at the examples though. Fine. And then in the theory, they've given there are 4 kinds of problems. The examples are in the slides. You could go through them. I did not write anything about this because I don't think. Not that they're not important. They're all a part of the syllabus. Who knows when sir's going to give a random theory question from a random slide. So essentially, any problem, for example, there is this n queens problem, there is this 853 jug problem. If any problem is there, you should be able to convert it to search problem. So it will have a set of states, it will have initial state, you'll have goal test, or you can simply write goal state, that is also fine. And then you'll have these transitions. If you're in a certain state and if a certain condition has been achieved, what will be the next state? Those are the transitions. And then path cost is essentially what is the cost of moving from one state to the other state. So if you're able to take a problem and define all of these aspects, then you will get your search problem. Examples are there in the slides. They were like vacuum world as a single state problem, vacuum world as a multi-state problem, 8 puzzle problem, 8 queens problem. There is script arithmetic problem, all those problems. And there's some problem with Romania. The examples are there in the slides. There's nothing much to be explained there. So this is representing a problem, that is fine. But how do you solve these problems? So we have different kinds of strategies. All of you know what these strategies are. Uninformed, informed. There's nothing for me to tell here. I will go through each one of them though. For the time complexity part at least. How do you compare two search strategies? So throughout for the next few pages, we'll be going through completeness, optimality, time complexity, and space complexity of each of these algorithms. So completeness is basically if at least one solution exists in the search space, then the algorithm should be then it is guaranteed that the algorithm will return a solution. If it can't do that, then the algorithm is not complete. The search strategy is not complete. Optimal is the solution returned by the algorithm is the best possible solution. You can't get any solution better than that. Time complexity, space complexity, it depends on the implementation. So there are three letters. B is max branching factor. Essentially, it's like the most number of children that a node has. That is max branching factor. Depth of least cost solution. I think these terms will make sense if you look at this one. When I said that when I said that to solve a search problem, you'll have to start from a start state and explore all its neighbors. If you keep doing that, you will get something that looks like this. No, you'll get a tree. So with respect to that tree, you have these terminologies. Max branching factor, which essentially states that if you pick any node, its number of children will be less than b, less than or equal to b. D, depth of least cost solution, is, for example, let's say this is a tree, a search tree, and your solution is here. So this is D. Depth, or let's say this is also a solution, but the depth of the least cost solution will make this essentially whichever solution is at the least depth, that depth becomes D here, depth of least cost solution. Max length of any path will be this one. Find the longest path, find its length, that will become M. This will be M. These letters will be used in the time complexity and space complexity analysis. If you open PPTs 3 and 4, there will be some theory about what is tree, what is search, tree search, what are the advantages and disadvantages of each of these search strategies. BFS, DFS, all of you know. But I'll talk about completeness, optimality, time complexity, and space complexity. So BFS will be complete if B is finite, which makes sense. Because if B is not finite, then you will keep going, you will keep exploring the same level for an infinite amount of time, and you will never reach this solution. But that's the thing, right? What does completeness state? If there exists a solution, then the algorithm should return the solution. It should be guaranteed, but there's no guarantee here. If the max branching factor is not finite, you will never reach a solution. So if it has to be complete, then B has to be finite. Is BFS optimal? It is optimal if the path cost is 1. What do I mean by path cost is 1? If you basically, this tree is there, no? The cost of each state transition is 1. So that is what I meant when I said path cost is 1. If it is not 1, then BFS is not optimal. You will see why. When we look at UCS, you'll understand. You can take any random example. Instead of path 1, you can assign 2, 3, 4, 5, 6. Keep assigning random numbers. You'll get an example where you can see for yourself that BFS is not optimal unless path cost is 1. Time complexity, see, how does BFS work? We'll start from the root node, then we'll look at its children, and then we'll look at children, and so on and so forth. In the worst possible case, each node will have B number of children. So it goes like this: 1 plus B plus 1 plus B, and then in the second level you'll have B square nodes. You keep adding. That's how you'll get all this, and that is how it becomes big O of B power D, where B is the max branching factor, D is the depth of the least cost solution. Space complexity is here in this case the same as time complexity. That is fine, but that is BFS. DFS, see, the thing about DFS is it will keep going down and down. So if the first path, if this path has infinite number of nodes, if it keeps going down, it will never reach this solution. That means it will not be complete. DFS will not be complete. So in order for DFS to be complete, it's the tree should be finite. It should not have infinite number of nodes. Like, it should not keep going down. So DFS is complete only if search tree is finite. It is not optimal because there's a possibility that you will give a solution that has a higher depth. For example, let's say this is G2. DFS will give this as the solution, but we know that this is the better solution. I don't think you'll have. I wrote the justification for those who want it. It's not like they'll ask you to explain the time complexity, space complexity. But if in case they ask you, you can just write what is time complexity, what is space complexity. So I've written the justification here. I'll not be explaining the justification because I don't think it is needed. But just remember the final answer. Depth limited search is basically DFS, but then you have a max limit. So let's say max limit is 2. So you will only be able to explore this much. You won't be allowed to go down. So if this is the goal, that's a problem. If the goal is below the depth limit, that will be a problem, right? Because this algorithm will not be able to give a solution despite the solution existing. So the goal should be above the depth limit. Only then DLS will be completed. It is not optimal. It's just like DFS. DFS is not optimal, so DLS is also not optimal, and its complexity will look similar to DFS. M is the max path length, right? The maximum path length. Like in the worst case, you will start from the root node and explore until the deepest node, and its length is m. So that's why DFS's complexity is b power m. I mean, justification is not required. So instead of m here, L is there because where L is the depth limit. I didn't write. L is the depth limit. Uniform cost search. Now this is optimal. This is nice. How does UCS work? You expand nodes closest to the start state until goal is reached. So if you have a start state, I have some videos that explain some of these search strategies. I'll share them with you. I found them on YouTube. But it's not that they're difficult. You should be able to do them by now. But anyways, I'll still share them. I mean, even you can find them on your own. So if you have a start state, you all know how do priorities, all of you must know how do a priority queue works, right? So when you start with a start state, you can dequeue it and then enqueue its children, and how will you enqueue them? You will enqueue them with respect to how close they are to the start state. Maybe diagram should help. So when you start here, you will then explore this one because this is the closest. And then the next closest will be this one. And then the next closest, let's say it's this one. And then the next closest is this one. And then the next closest is this one. The next closest is this one. That is how UCS works until the goal is reached. Examples are there in the slides too. You could go through them. If in case you need any specific examples after the meeting is done, I could write them and then post them probably. Time complexity, you can try remembering or you can go through the explanation. Nothing much to be discussed here. See, but here UCS, the thing about UCS is the path cost need not be 1. This works for any path cost. So BFS is essentially a special case of UCS. If there is a uniform path cost in UCS, it would become BFS. or it need not be one, it just has to be uniform. Optimal if path cost is uniform. Iterative deepening depth first search. Essentially depth limited search, but then you keep iterating. First you'll keep L equal to 1, then L equal to 2, L equal to 3, until the goal is found. Here the good thing is you will not, even if there are infinitely many nodes, you will not keep going down, because there is a limit at every iteration, which makes it better than DFS. But about advantages and disadvantages, they're there in the slide, you could go through them. When is this complete? How does this work? IDDFS will look like this. When depth limit is 1, you will perform DFS on this. When depth limit is 2, you will perform DFS on this. That's how it goes. Again, if B is not finite, then the DFS will keep going on. Let's say the root node itself has infinitely many children, then DFS will keep going on. It will never end. So again, what is complete? Complete is basically if the solution exists, then it should be guaranteed that the algorithm returns the solution. If it doesn't, then it's not complete. I mean, explanations I don't think are necessary for this. You can just go through the time complexity if they ask you. Bidirectional is you start from the goal node, you also start from the you start from the initial node, you also start from the goal node. Finally, after some time, both the searches will meet at one intersecting node, which will terminate the search, and then you can therefore declare some path is found. I do not have explanations as to why BFS makes it optimal, but I think complete you can understand, because whenever the from initial state, when you reach the intersecting state, and from the goal state you reach the intersecting state, you can for sure say that there is a path from the initial state to the goal state, which makes it complete. So as long, whichever search you use, as long as both these searches meet, it becomes complete. But it seems like using BFS will guarantee that both these searches will meet, which makes it complete. So justification I'm not giving, I did not go through them as well. But the time complexity is interesting because you're searching from both the sides, right? Simultaneously. That's why you have d by 2 here. You're not exploring the entire depth. You only explored half of it. The other half also happens simultaneously. So it's d by 2. Those were uninformed search. We have informed search now. Basically you have extra information. Later we'll see it is called heuristic. We'll see what it is. The first thing that we have here is best first search. By definition, what does it do is it expands the most desirable unexpanded node. And how do you know which node is desirable? You have a function called f of n, and it is called evaluation function. Now, depending on what this f of n is, this best first search can have different names or different types. There is greedy best first search, and there is also A star, which is also a kind of best first search algorithm. But I'll give you an example that is familiar. So let's say f of n is nothing but the cost from the initial node to the current node. Then that would make this best first search UCS algorithm, because how does UCS work? Uniform cost search. It will expand the nodes that are closest to the initial node. So in best first search, if you keep f of n as a cost from initial node to current node, and if you want f to be as low as possible, then the search is nothing but UCS. But it is still uninformed because we are not adding any new information. We will see what will happen if we add new information. So if f of n is equal to some h of n, where h of n is called the heuristic, and in this case heuristic is nothing but the estimate of cost from the current node to the final goal. So if I draw a search tree, and let's say goal is here, when you explore a search tree, you will only know the costs that you've incurred only up until the nodes that you've explored, but you do not know what's going to happen. You do not know how much, you do not know the exact cost from the current node to the goal node. You do not have that information because you did not explore it yet, so you do not know what that cost is. But you can estimate, you can provide an estimate. For example, in this search tree, how can I provide an estimate? What I can do is I can check, I can find out the straight line distance. So I can find out what is the straight line distance from this node to the goal node, from this node to the goal node, from this node to the goal node, this node to the goal node, this node to. So I can provide heuristics for every single node. In this case, the heuristic is what is the straight line distance from the current node to the goal node. That is one possible heuristic. Depending on the problem, the heuristic can change. But it is in general, how much, what is the cost, what is the estimated cost from required for me to transition from the current node to the goal node. So by definition, if your evaluation function is nothing but this heuristic, here you're not checking how much cost you have incurred until now. You're only checking what is the cost from the current node to the final node. That makes it greedy best first search. If you look at the evaluation of this search strategy, is it complete? No, it's not complete. There are cases where it can go in loops, and there are cases it is not guaranteed to give an optimal solution. See, it's not even complete. How can it be optimal? It can't. Time complexity, space complexity, it's similar to DFS because it behaves. Does it behave similar to DFS? No, I'm not thinking about the justification. I did not think about the justification, but these are the complexities. Now the other kind of informed best first search algorithm is A star algorithm. In A star algorithm, what you do is instead of being greedy, you will also check what is the cost incurred until now. So in UCS, we had this. In UCS, we checked what is the cost from the initial node to the current node. In greedy best first search, we were only looking at the heuristic. What is the cost from estimated cost from the current node to the final node. In A star, what you'll do, you'll add both of these two values together. So you'll also check, you'll basically check the sum of the cost incurred from start node to current node, and you'll also you'll also check what is the estimated cost from the current node to the final node. I think you know how to solve A star. That is fine. Just keep expanding the nodes whose f values are the least. That is essentially how you're supposed to solve best first search. So is A star complete? A star is complete unless something happens. So let's say there are many nodes in the search space whose f value is less than the f value of the goal. Because best first search operates in this way. It will keep expanding the nodes whose f value is small. But if there are infinitely many nodes whose f value is smaller than f value of g, then best first search algorithm will keep expanding these infinitely many nodes. It will never reach g. So that means despite there being a solution, you're unable to return that solution. So A star will not be complete in that case. Apparently, A star is optimal when it is complete. Why is it optimal? I am not sure, but it is optimal. I do not have the justification. Time complexity, some exponential time complexity, probably B power D. Space complexity is also almost same. That is fine. Heuristic properties. This one very colorful. You'll have to know probably. There are three properties. We'll first look at the first two: admissible and consistent. So heuristic, I told you, heuristic is the estimated cost from current node to final node. If the heuristic value is less than or equal to the true value, then the heuristic is admissible. Basically, there is no overestimation, and there is a theorem that states that if the heuristic is admissible, then A star using tree search will give you optimal solution. I don't have justification. It's a theorem. There is no justification in the slides too. The other heuristic is consistency. So you have this strange looking inequality. What does it do is, let's say you are at node n, and if you perform an action A, you move to node n prime. So they are neighbors. So n prime is a neighbor of n. So what you're checking is, you're checking the heuristics of the current node. You're checking if the heuristics of the current node is less than or equal to the cost incurred while transitioning from node n to n prime, and the heuristics of the new node. Basically, if you satisfy this inequality, you can say that your heuristics is consistent. Mind you, this should be true for every n prime. So if you perform any action, if you perform all sorts of actions while you are at state n, you will be going to many other n primes. So it could be n prime 1, n prime 2, n prime 3. For all those n's, and or simply you can say for every state, this condition has to be satisfied. Only then the heuristics is consistent. All possible combinations you have to see. So the heuristics of the current node n should be less than the sum of the heuristics of the next node plus the, I told sum, no? So sum of the heuristics of the next node and the cost of transitioning from the current node to the next node. A is just an action. You did something, you're going from the current node to the next node. There is one more theorem. It states that if you know that heuristics is consistent, you use A star. Using graph search for A star will give you optimal solution. I do not have the justification for this as well. The other property is dominance. So basically, if one heuristic is greater than the other heuristic, then that heuristic is dominant. Or in other words, you can say it is more informed. But one more thing is, if H2 is dominant, and if both H1 and H2 are admissible, admissible, it means it is not overestimating. So if it is admissible, then H2 is preferred for search. It will give you more better results. For this one, I don't think you need any proof. You can think about it. It seems commonsensical. Then okay, further you have relaxed problems. Basically, you drop some constraints. If you drop some constraints in a problem, it becomes a relaxed problem. The context of relaxed problem in AI is, if you're unable to solve a problem, what you're supposed to do is you drop the constraints and then solve the problem, and whatever solution you get, use them as heuristics. That was the point here. Cost of the optimal solution in the relaxed problem can be used as heuristics for the original problem. That was all about relaxed problems. The theory is there in the slides. And then we were introduced to local search algorithms. There were two of them, hill climbing and simulated annealing. I think simulated annealing is a part of local search. If it's different, it's fine, but I kept them under local search algorithms. Local search algorithms, you're least bothered about the global optimum. You're only searching for locally optimal solutions. Hill climbing, you have three kinds of hill climbing: simple, steepest, stochastic. Simple is basically, let's say you're starting at the start node, and then you will generate all its neighbors. Then one by one, you will keep checking: is this neighbor better than the current state? Is the neighboring state better than the current state? And the moment you find a neighbor that's better than the current state, you will update the current state to the neighboring state and start exploring from there. How do you compare two states? You look at the evaluation function. So let's say some f of x or f of n, whatever is there. There is an evaluation function. So if you want to maximize f, then whichever state gives bigger f, that state is the better state, right? That is ascent. Descent means f. You have to minimize f. We've done something similar to this in the previous semesters. Steepest hill climbing is instead of picking the better neighbor, go through all the neighbors and pick the neighbor that gives you the best evaluation function value. That is steepest hill climbing. Stochastic hill climbing is similar to simple, but what it does is it's not going to go in an order. It will randomly generate a neighbor and then check if it has a better evaluation value or not. If it doesn't have, then it will generate one more random one. So it will keep generating random neighbors until it gets a better neighbor. So there's no guarantee that it's the best neighbor. It's just that randomly it will generate neighbors. The moment it finds a better neighbor, it will update the current state to the neighbor state and then repeat the process. There is some theory about the limitations of hill climbing. You can see in the slides. The PPT5, I think PPT5 has theory about simulated annealing. There is a lot of theory about what annealing is in real life. But at the very end, there is a problem related to simulated annealing. So for that problem, I've given information in this notes. So if you wish to read the theory, you can read. I do not know what kind of theory questions will be asked from there. It's just a lot of theory. But okay, I will go into the problem part. Simulated annealing. How do you solve simulated annealing? Before knowing how to solve simulated annealing, let's see what is there in simulated annealing. What is there in the algorithm? So there is some objective function f which you want to reduce. There is an initial solution. So in local search problems, that is how it is, right? You begin somewhere. So you have an initial state or initial solution or whatever. Let me write state. You have an initial state. And then there's something called temperature. When you look at the algorithm, you'll probably understand what this temperature is doing. But we have initial and final temperatures. Initial temperature will be maximum, final temperature will be the minimum. And since we are dealing with temperatures, there's something called cooling condition. Essentially, we'll be updating our temperature values when and where we will see in the algorithm. So how do we update the temperature? We'll multiply the temperature with a number that is less than 1, a positive number. So temperature keeps decreasing. We will see how and when in the algorithm. And there's something called equilibrium state and stopping condition. Stopping condition is essentially whenever t reaches a value that is less than t min, then you stop the entire algorithm. Equilibrium state we'll see. we'll see. I will explain it within the algorithm. So how does simulated annealing work? You begin with your initial state. So let's say S is the state that we're talking about. You initialize it with Si, which is your initial state, and you set the temperature to the initial temperature, which is Tmax. That is step 1. Step 2 is now you randomly generate a neighbor. Now, depending on the problem, you will be able to randomly generate a neighbor. If you look at the slides, there is a bit string, I think 5-bit string. So how do you randomly generate a neighbor there? You flip a bit. You randomly flip a bit. Which bit? Your wish. So in the example, you will be able to recognize in the slides which bit has been flipped. Why only that particular bit has been flipped? There is no reason. It's just random flipping. So it's random. So first you have to get this into the mind, because there were cases where I was asked why only this bit got flipped and things like that. So second step, randomly generate a neighbor. I'm calling it S prime. And then you have to calculate something called delta E. If you read the theory before, you'll understand why all these terms are coming. But in order to solve the problem, you don't have to know anything. If you follow this algorithm, you'll be able to solve simulated annealing problems. So delta E is nothing but the difference between the evaluation functions of the neighbor and the current state. So what is our objective? Our objective is to minimize f. And if our neighbor's f is smaller, we will be very happy. So in other words, if delta E is less than or equal to 0, it means the neighbor's f value is smaller or equal to the current f value, right? If this is negative, it means neighbor is either better or exactly equal. So if that is the case, we will update our neighbor. We will update our current state as the neighbor state. But in case delta E is positive, it means the neighbor is at a much worse position than the current state. If it were hill climbing, we would have ignored this state, but the property of simulated annealing is it will allow worse moves. It will allow worse moves. That's the property. It will allow worse moves. So what do you mean by allowing worse moves? It means even if the neighbor is at a much worse position, there is a possibility that we might transition to that state. The reason why we are doing is wait 1 minute. Okay, where was it? So simulated annealing allows worse moves because because of this property, it is able to escape local optima. If you are using hill climbing, there is a possibility you will get stuck in local optima and you will not be able to reach global optima. But simulated annealing is different. So by allowing worse moves, it will be able to jump out of local optima. So how do we allow worse moves? We accept if delta E is positive, then we accept the neighbor with a certain probability. In the example given in the slides, I think they've kept a threshold. If the probability is more than 0.5, accept it. If it is less than that, don't accept it. You can follow this threshold thing. Now after step 3, what do? You look at step 4. It says if equilibrium condition is not met, go to step 2. Equilibrium condition is usually number of iterations. For example, for a certain temperature, we are at temperature Tmax, no? for a certain temperature T, you repeat this process like 10 times or whatever. It's usually that way. For simplicity, you could just think of it as just one iteration probably. So let's say max iteration is 1. So if one iteration is done, move on to the next step. Or if max iteration is 10, if the current iteration is 1, it means equilibrium condition is not met. You keep repeating this process until you reach 10 iterations. So it depends. I think in the example given in the slides, there is no equilibrium condition. That would mean there's only one iteration as far as I remember. But anyways, so if there are, let's say 10 number of iterations, you will keep repeating this process. You will keep generating random neighbors and you will keep updating your current state. So finally, after the equilibrium condition is met, in step 5, you will update your temperature. How will you update your temperature? You will replace the current temperature with some alpha times the temperature. So what is the alpha? It will be already given in the cooling condition. It will be some positive number less than 1. So if temperature let's say is let's say 500 and alpha is 0.1, then your alpha is 0.9, then your new temperature will be 0.9 into 500. And after you've updated your temperature, you check if your stopping condition is met or not. So stopping condition is if your new temperature is less than minimum temperature. Minimum temperature is already given. If that is not the case, then you repeat the entire process. You go back. You repeat the entire process. So you keep doing this until temperature goes below T min. Finally, whatever is S is the solution. This is simulated annealing. Would have been better if there were examples, but there was very little time for me to write examples. Maybe I'll try writing them later. After this meeting is done, I'll upload probably. Now in PPT 6, we have a constraint satisfaction problem. There is theory as to what is a constraint. You can read in the slides. There's something about constraint satisfaction problem. That's the main thing. So constraint satisfaction problem, basically you have a problem and then you have constraints. You have to satisfy those constraints. So the three main things are, you have variables, x1, x2, x3 or whatever. You have some variables and you have some domains for each of these variables. So in these domains, you will be having all these values that you can substitute in each of these variables. And constraints are basically you have all these variables in some form of equality, inequality, and anything, whatever it is. So if you're able to express a problem using variables, domains, and constraints, you will have successfully written down a constraint satisfaction problem. For example, we have a map coloring problem. You can express it using constraint satisfaction. You can write the variables, you can write the domain of each of those variables and write the I think we'll see. I'll show you the CSP of map coloring. State of the problem. See, we've been talking about states. An environment has states. So states keep changing. So we were talking about how agents perceive the environment, they perform some action and change the environment. So similarly, there's no agent here though, it's just a state. So in this context of constraint satisfaction problem, what is a state? So if you assign values to some or all variables, that becomes the state of the problem. You can have multiple states and there are different kinds of assignments. So when you're assigning values to variables, how are you assigning values? From the domain, you will pick the values and give it to the respective variables. So when you're making assignments, if no constraint is violated, then the assignment is called consistent or legal. And if each and every variable is assigned some value, irrespective of whether the constraint is satisfied or not, then the assignment is called complete. If the assignment is both consistent and complete, then it is called a solution. So solution is basically every variable is assigned a value and all these values are satisfying every constraint. So consistent means every constraint is satisfied, complete means every variable is given some value from their respective domains. So for example, let's take map coloring. I have Australia here. So we need to define what the variables are, what the domain is, and what the constraints are. So if you look at the map, you have 1, 2, 3, 4, 5, 6, 7. You have 7 regions in Australia. You could treat each one of them as no. First of all, what is the map coloring problem? Map coloring problem is this one. Any two adjacent regions should not have the same color. So you have to represent this in terms of CSP. How do you represent? You can define each region to be a variable. So you have WA, NT, and all those variables. You have 7 variables. Now domain is the set of all values that a variable could possibly take. In this case, we are defining the set of colors to be red, blue, and green, and every region could take each of these variables. So it's in this case alone, the domain is same for every variable, but in general, each variable will have its own domain. They need not be the same. In this case, the domain is same. It means any variable can take it means any of these variables can take any value from the domain. So WA could be red, NT could be blue. You get my point. The third thing is constraints. Now what is the constraint? In English, the constraint is adjacent regions must have different colors. How do you represent it in CSP? You can take an example. So let me take two adjacent regions. For example, WA and NT. WA and SA, they are adjacent regions. How do you say they must have different colors? You can simply write WA is not equal to NT. So how does it make sense? So for example, if WA is red, it means NT can't be red. So how do you represent it symbolically? You have to write WA not equal to NT and WA not equal to SA. But this is not the only constraint. You have to write all possible combinations. So WA not equal to NT, WA not equal to SA. And you don't have to write NT not equal to WA, that is already covered. NT not equal to SA, NT not equal to SA, NT not equal to Q. Like you have to cover all pairs here. NSW not equal to V, NSW not equal to SA, NSW not equal to Q. You have to write all the constraints. For example, here WA not equal to NT and WA not equal to SA. It's just an example, but constraints means you have to write all possible constraints. This is your CSP. How do you represent the problem? You have something called the constraint graph. Basically, if you have first write down all the variables, they become your nodes, and if any two nodes are related, if any two nodes are related in the sense, if you find them in the same constraint. So let's say constraint C1 is in between WA and NT, or let me take this example only. WA not equal to NT. Let's say this is constraint C1. So in the constraint graph, what you're supposed to do is just take a line and join WA and NT. WA and NT. So this is constraint C1. You don't have to mention what the constraint is. You just have to join the variables that are involved in the same constraint. So if you look at this constraint graph, it is very much obvious because constraints are in between two adjacent regions, and you can see each of the edges join only those nodes that are adjacent to each other. You don't have a line from WA to V because they're not adjacent. And because they're not adjacent, there is no constraint. Because there is no constraint, there is no edge. And T is standalone. It is not adjacent to anything, so it has no edge incoming or outgoing or whatever. One more thing is, if you paid attention, in this map coloring, each constraint is containing at most two variables. Only two variables are there. You don't have three variables. If you write down all possible constraints, you'll only have two variables in each constraint. So that would make it a binary CSP. And it is easier to draw because binary CSP means you just have to join two nodes. But what if it is a higher order CSP? It will be difficult for us to draw constraint graphs, and I don't think there is any example of higher order constraint graphs, so I will not be talking about that. So there are different varieties of constraint satisfaction problems. Like you have unary constraints, binary constraints. Map coloring is binary constraint satisfaction problem. Because let's say this is a constraint for a different problem. How will we be able to draw the constraint graph? Because an edge joins only two nodes, right? It can't join three nodes. That is not possible. They have different representations, which is not in the syllabus, so I'll not be covering that. So varieties of CSPs. The values could be discrete, they could be continuous. Discrete means, for example, colors, red, blue, green. These are discrete. But if you take the entire spectrum of colors, probably it's continuous, because you could always make a new color within the entire spectrum. Because RGB, right? And then I have infinitely many numbers in between 0 and 255. So I theoretically have infinitely many colors. Theoretically, I don't know. I don't think the computer has infinitely many colors. There'll be some limit. Or let's say you're dealing with time. Time is continuous. So that is there. Continuous in the sense it's not like red, blue, green. It's like 1, 1.1, 1.1. You get my point. So we've seen how to represent the problems. Now how do we solve the problems? There is a kind of an algorithm that's called generate and test algorithm. What does it do is, it will simply find out all possible assignments. I told you what assignment is. Assignment is basically you take values from the domain and give it to each of the variables. Complete assignment means every single variable has some value from the domain. So it will generate all possible complete assignments and then one by one check which complete assignment is consistent. Consistent in the sense which of these complete assignments is satisfying all the constraints. And the moment they find a consistent complete assignment, that means you have your solution. But this is very inefficient because there are better ways of solving it. One better way of solving it is using search algorithms. So how do you use search algorithms? So we will create a search tree and it looks something like this. So initially, before getting into initial node, we'll first have to I'll first have to tell you, how does this search tree look like? How does a typical node in this search tree, how is it going to look like? This search tree is going to be used to solve CSPs. So how is this search tree going to look like? So a typical node in this search tree that solves a CSP looks like this. You'll have assignments. So let's say you have n number of variables, but only k of those variables have been assigned. So you have some values v1, v2, v3 till vk. You still have other variables that have not yet been assigned. So what you will do is you will generate neighbors. And a typical neighbor of this node will look like this. So how do you generate a neighbor? Essentially you write the same you have the same content, so the same assignments you have from the previous node, but the new thing is you the neighboring node will have an extra assignment. The extra assignment is capital Y equal to small yi. So capital Y is that is capital Y is a variable that has not been assigned yet. So if you look at this node, if you look at the parent node, you can see that x1 to xk have been assigned some values. So you have to find a variable y that has not been assigned yet. So it should not be x1, it should not be x2, it should not be xk, it should not be any of these values. So y should be a variable that has not been assigned any value. And of course, yi should belong to the domain of y. That is where you're going to get your values from. So after you make this assignment, you should also ensure that the assignment is consistent. So basically, when you create this neighbor, you have to check if all the constraints are being satisfied. And if it is being satisfied, then it is a valid neighbor and you can add it to the search tree. There will be many variables that have not been assigned any values, and there will be many values that you could possibly assign to that particular variable. So you in theory you will have many neighbors of a certain node. For a certain node you will have many neighbors, and you can add all of those neighbors, and then you can continue the same process again and again. So initially you will have a node that has no assignment, then you will pick one variable. So let's say you'll pick x1 and then you'll assign it a value. So this is one assignment, and then you'll keep expanding. Then you'll go to x2, then you'll go to x3, then x4. You'll keep continuing, ensuring that the assignment is consistent. So when will this search end? The search will end when a node gets complete assignment, because we know that in the search tree every node is consistent, and if you get consistent and complete, it means you got a solution. So this is how you solve a CSP problem using a search algorithm or search tree. We've seen many search strategies. You can use any one of those, but in general, this is how you solve CSP using search. But apart from that, the more important things are arc consistency and all that. No. Before getting to that, let's see constraint propagation. Constraint propagation is basically you look at the constraints and remove values from the domains which you will never be able to assign to the variables. Maybe if there's an example that I could show, it would be much better. After the meeting ends, I will continue writing so that I could show some examples. Because today's meeting is very short, I have nothing much to show. Anyways, constraint propagation. I'll show some example later. But if you get the theory part, basically go through the slides. You have some theory over there. Constraint propagation is essentially you will be communicating the domain deduction. So domain deduction is basically you're removing values from the domains which you can never assign to the variable because they will potentially be violating the constraints. How I wish there was an example here, but I'll write an example later. Constraint propagation will reappear, that's there. Backtracking is something very similar to DFS. It is similar to this solving CSP using search. It is very similar. I think it's almost the same, I guess. There's a video, I'll share that video. It's just 5 or 7 minutes long. There's nothing much in that. I mean, backtracking is probably, it's like you start with no assignments and then you assign a certain variable x1 is equal to v1, and then you check if all constraints are satisfied, and then along with x1 equal to v1 you assign a new variable x2 equal to v2, and then you check if all the variables are being satisfied. If it is all the constraints are being satisfied, if they're not getting satisfied, then change the value. find another, and so on and so forth. And if you reach a dead end, then you backtrack and move to a different path. So it's like DFS. Backtracking is like DFS. The video is much simpler. You can see how backtracking is done. But that's just simple backtracking. There are ways to improve the backtracking search. Is there space anywhere? Okay. So if you remember the search tree, you start with no assignments, and then you will assign one variable some value. You will check all the you'll check if the assignment is consistent or not. Then you will assign one more variable. Then you will check if all the assignments are consistent or not. And if they are not, you will leave that branch, and then you will go to a new path. And you'll keep exploring. You'll keep expanding. And the moment you reach an assignment that is not consistent, you will leave that, and then you will go to a new thing. So it's almost like DFS. And if you reach a complete assignment, then you backtrack. I think the video should help you. I'll share the video, or I'll write examples later and send. But there are better ways of searching for a solution than backtracking also. There are ways to improve the backtracking search, because while doing backtracking, when I said you have a search tree, you start from an initial node, and then you'll have to expand into all the neighbors. Which neighbor should you expand first? Like, let's say you have 4 neighbors. Which neighbor should you explore first? In backtracking, in simple backtracking, you will just start with the first one. But there are ways to improve this backtracking. So if you ask this question, which variable to be assigned next? After assigning x1, should I assign x2 or should I assign x3? Which variable should I assign? So there is something called minimum remaining values. Wait, can I copy my Australia? If you open the slides, I think there is an example. There's a picture associated with this minimum remaining values. So choose the variable with fewest legal values. Minimum remaining values is also called as most constraint variable. Let me see if I can give an example here. Choose the variable with fewest legal values. Let's say this is a map coloring problem. So you have red, green and blue. So let's say this is the current state. This is the current state. So what is state? I told you, in CSP, state means assignments made to some or all of the variables. Here 2 variables got assigned green and red. So this is partial assignment. So this is a state of the problem. We're in some state. And RGB, we know it's a domain, domain of every variable. So if you, let me call this A, or let's say 1, 2, 3, 4, 5. So you have 5 regions. Variable 2 and variable 4 are assigned 2 colors, red and green. Now from this state, how should I go to the next state? Should I assign value to 1, 5 or 3? Should I assign value to 1, 5 or 3? If you look at 1, in 1 I can put RGB, there is no restriction. Anything is fine because all constraints will still satisfy from if you look at the current state. If you look at variable 3, I can still put RGB, there is no problem. Or let's say this line is also there. If you look at variable 3, I can't put R because it will clash with variable 2. So my domain of 3 will be G and B. But if you look at variable 5, I can't put R because it will conflict with variable 2. I can't put G because it will conflict with 4. The only value left for variable 5 is B. So for variable 1 we had 3 possible values. For variable 3 we had 2 possible values. For variable 5 we had only 1 possible value. So if you look at the remaining variables which have not been assigned, the variable with the minimum remaining value should be picked. Choose the variable with fewest legal values. So in this particular example, the variable with the fewest remaining value is variable 5. Only one remaining value is there. So here 5 is the MRV, minimum remaining value variable. So you will pick this node and you will assign it. Now you will assign. So since there is only one value, you will assign this one value only. There could be some other cases where you'll have multiple values, but still it has to be the least. So it could be 10, it could be 30 here, 10 here, 20. Still here variable 5 is the least. Variable 5 is the variable with the minimum remaining values. So you'll have to pick one value out of those 10. Fine, but let's say in the same example, let's say okay, I'll remove variable 4. So this is a new problem, no? I changed something, so this is a new problem. This is we started somewhere. So this is the current state. Which variable should I assign next? If you look at variable 1, you have 3 possible values. If I look at variable 5, I have 2 possible values because I can't put R. It will clash with variable 2. If you look at variable 3, you still have 2 possible values. But now I can't apply my MRV because both variable 5 and variable 3 have the minimum remaining values. So in case of a tiebreaker, you will use degree heuristic. In case of a tiebreaker, you will use degree heuristic. So whichever degree heuristic essentially states that whichever node has more number of variables, you take that. So that is why you have degree here. Whichever node has more number of variables. So neighbors. So what do you mean by more number of neighbors? It basically means that that variable is involved in multiple constraints. Choose the variable with most constraints on remaining variables. So for example, let's see. Choose the variable with most constraints on remaining variables. So essentially, find the variable that appears in most of the constraints. So how do you know that? If you look at the constraint graph, which is here, you can notice variable. Wait, Let me use a different color. So how many constraints is variable 1 a part of? Only one constraint, because there's only one edge. Variable 5 has 3 edges around it, so it is a part of 3 constraints. Variable 3 is a part of 2 constraints. It has only 2 edges. So using degree heuristic, now you can safely say, you can safely assign the value to variable 5. Initially using MRV, you were unable to assign any value because variable 5 and variable 3 had the same number of remaining values. So since there's a tiebreaker, you can use degree heuristic. Choose the variable with most constraints on remaining variables. So every edge in this constraint graph represents a constraint, right? So variable 5 is the variable that has most number of constraints on remaining variables. So 5 and 1, 5 and 2, 5 and 3. So it is variable 5 is a part of 3 constraints. It is putting a constraint on variable 1 also, variable 2 also, variable 3 also. So 3, variable 5 has 3 number of constraints. Variable 3 has 2 number of constraints. It's putting constraint on only variable 2 and variable 5. Variable 1 only, it's asserting, it's putting its constraint only on variable 5. So again, safely you can say, you can assign variable 5 your value. Okay, done. What if you have a tiebreaker in that also? I don't know. But as far as this is concerned, if one works, it works. If it doesn't work, go to point number 2, degree heuristic. Fine, this is for choosing which variable to assign next in backtracking. Now, previously I told there could be a case where you have 30 colors here, 20 colors here, 10 colors there. Then out of those 10 colors, which color to pick? Which value to assign next? So there is a rule for that also. It's called the least constraining value. So these two rules are for variable selection. Now value selection. Which value to assign? So least constraining value states value that rules out fewest values in remaining variables upon assignment. Let's see if I can make an example. Let's say this is some state, and let's say this yellow variable, this yellow node is the variable that you're supposed to assign. because you will only assign a value after you fixed which variable to assign, no? So after you fix the variable, you'll have to decide which value to assign. So this yellow node has two options. It can either take red or blue, right? So there are two possible cases. So which one should I take? Should I take red or blue? In this case, if I take red, what will happen? Let me make two cases. So, okay, something is there. I feel like OP sir now, but okay. So let's say you want to assign red ones, you want to assign blue ones. If I assign red here, now I'll have to look at how many values can I put in the other variables. Here, if I look at this node, how many values can I put? R I can't put, G I can't put, blue I can put, so 1. 1 is remaining, and here how many? R I can't put, B I can put, G I can put, 2 is remaining. They're remaining, I didn't rule them out, they're remaining. In the other case, if I put B here, R, G, B, here I can't put anything, here 2. Initially here 1 is there, here 3 is there. So initially here I could put 1 value, here I could put 3 values. But if I put R here, here it still remains 1 value. Here I can put 2 values because here I can't put R. So 3 became 2. Here how many values did I rule out? Here I ruled out 1 value. Here I ruled out 2 values. 1 is 1, that is fine. 3 is 2. 3 became 2. It means I ruled out 1 value. 1 is 0. I ruled out 1 value. 3 became 2. I ruled out 1 more value. So 2 values I ruled out. So which is the assignment that has the fewest number of ruling outs? It is this one. You ruled out only 1 value. See, this is one way of looking at it. There is one more way. Instead of looking at how many colors you have ruled out, you can also look at how many values are remaining. Instead of choosing the assignment with the fewest, with the minimum ruling out, is equivalent to choosing the assignment with the maximum remaining values. Here the remaining values, if you see, it is 3. Here it is 2 plus 0, 2. So maximum remaining values is there in the first case. So it's still the first case only. So this will be your least constraining value. So assigning R here is the next course of action. So here your R is the least constraining value. By assigning R, very few colors are getting ruled out, which is only one color is getting ruled out. But if you assign blue, 2 colors are getting ruled out, which we don't want. So this is how you pick your values. Once you fix which variable you're going to assign a value, this is how you select your values. Fine. Using these 3 things, you should be in a better position. You should be able to do backtracking in a better way. There is an example in the slide that takes I think almost half the PPT. It is that long, I think. You can go through that example. Okay, not half. Okay, not half. Some. Okay, my bad. Not half. Because there were PPTs where half the content was just search algorithms. I spent time here because you will be using backtracking, I think. Fine. Forward checking. Forward checking is basically whenever you make an assignment, you will go through all the domains of the remaining variables and check if any value is inconsistent. Inconsistent in the sense it doesn't satisfy the constraint. So let's say an assignment is made. Let's say I am using the search tree representation after an assignment. Okay, fine. My search tree. I'll give examples later, but if you are able to understand theory, after an assignment is made, I will go through all the domains of the remaining variables and see which value upon assignment will cause inconsistency. So before even assigning values to those unassigned variables, I will remove the values from their domains, because I know it is pointless. Those values can never be assigned because it will never satisfy the constraint. If I will, okay, example is in the slide. If you do not understand the example, I'll make an example document and upload it tonight, or tonight only I'll upload. But that is the essence of forward checking. And then you have consistency algorithms, which is apparently more better than backtracking. You have AC2, you have AC3, and all those, which we'll come to soon. Apart from constraint graph, you have something called constraint network, which is different. It is different from constraint graph. Here you will be specifying what the constraint is as well, but you have a slight change. In constraint graph, nodes are variables and edges are constraints. Here everything is a node. Nodes are nodes. Oval nodes represent variables, rectangular nodes represent constraints. Edges do nothing, they simply join the variable and the constraint. They simply join rectangles and ovals, that's it. But in constraint graph, the edge represents a constraint. So this is constraint network. Constraint graph will look something like this. This is constraint graph. So if you want to convert the constraint graph to constraint network, you have to replace all the edges with two edges and a rectangle in between, and in the rectangle you have to write what the constraint is. Hmm. 5 to 6, 6 to 7. Instead of explaining what AC2 is, I will solve an example and upload it. That would be much better. And for AC3, I think I found a video, so I will share that as well. So I will stop for now and continue writing this notes. So, and I'll try adding examples so that it becomes easier for me tomorrow. Okay, fine. Let me just tell you what this AC2 means. Example, I will upload it soon. Maybe I could solve minor 1 and minor 2 paper and upload that. That would be better. So there is a different meaning for consistency in the context of AC2. AC2, you will be dealing with two variables. So there is an arc called x to y. It is different from y to x. So you have to be careful. So I will tell you what is the meaning of consistency in AC2 and end this live stream. I will continue with the other topics tomorrow. I will let you know when. Okay, consistency in AC2. So you have two variables x and y, and there is an arrow from x to y. The direction is important. Y to x means that is different. So when you have arc x to y, that will only be consistent when for every value belonging to domain of x, there exists at least one y that belongs to domain of y that is consistent with x. Too many symbols. If I could show you an example, if possible. A simple example will do, I guess. let's say you have three regions and each of the variable has domain RGB. I will only show you one consistency example and then I think I will end the video. If the first variable has R, it means G and B are out of the question. Oh, wait. This is that Australia example only. So for the Australia map, what I've done is I've assigned two colors to two variables. This is the current state. You can look at the domain of every variable. R is R because it is R. This variable has G, so it can't have anything else in its domain. In this variable, you can't have R, you can't have G. You can only have B, so in the domain B is there. In this also you only have domain B. In its domain you have RB because here G is there. Here there is no restriction, so RGB. In this domain also RGB. So this is the current state. I am showing you all the domains also. So we will look at R consistency between SA and NSW. So we'll have to check if SA is consistent with NSW. So how do we know if SA is consistent with NSW? You will have to check for every value in the domain of SA. So for every value in the domain of SA, here only one value is there, so which is nothing but B. So you have to check for B. So if SA is B, if SA is B, is there any value in NSW that satisfies the constraints? So if SA is B, what value can NSW take? It can't take B because they're neighbors. It can take red. Then NSW can take red. So that means there exists a value in NSW such that the assignment is consistent. Because we are able to find this for all values in the domain of SA, which has only one value, this arc is consistent. Now check if you check the other way around. Let's see if it is consistent the other way around. Is the arc NSW and SA consistent? So you'll have to look at all values in the domain of NSW. In NSW you have R, you have B also. You have R, you have B. Now you have to check if for each of these assignments you have some consistent assignment for some consistent value for SA. So if NSW is R, I can give SA as B. This is fine. If I give NSW as R, I can give SA as B. No constraint is violated. But now the problem is, if NSW is B, SA will not have any valid value. I can't give anything to SA. So here we are failing the AC to arc consistency condition. We are failing this condition. And if the arc consistency is failing, then we are supposed to do something. What we are supposed to do is you have to propagate the constraint. So there is a way to propagate the constraint. You have to check certain arcs. What those certain arcs are, you'll have to check all the arcs that okay, fine. This is satisfied, this is not getting satisfied, no? So where is it not getting satisfied? It is not getting satisfied in this place. So what you do is you remove the value from the domain of NSW. So NSW, from its domain, we will remove the value B. After removing the value B from the domain of NSW, now you're supposed to do constraint propagation. So you will have to look at certain arcs. Those arcs will look like this. Or since NSW lost the value from its domain, you have to check the consistency of all the arcs that look like this. Variable arc NSW. So if you look at NSW, what are the arcs? You have, or let me call it Z. Oh, this is variable Q. This is variable V. So if you look at the neighbors of NSW, you have Q, SA and V. So you'll have to recheck the arcs Q, SA and V. Why are we checking these arcs? Because if you look at the consistency condition, here NSW lost one value. When it loses one value, there is a possibility that this whichever Y is satisfying the arc, that could have disappeared. That's why we have to recheck these arcs. That is the reason, but you don't have to know the reason. So here what did we do is we started with a state. Here WA was assigned R and Q was assigned G, and then we were checking certain arcs. So we were checking if SA was consistent with NSW, and we were checking if the arc NSW SA was consistent as well. So how do we check that? We have to look at all possible values in the domain of NSW. In this case it was R and B, and we have to assign it to NSW, and we have to check if there exists any valid assignment for SA. When NSW was R, SA equal to B is a valid assignment. But when NSW is B, SA was unable to take any value. So because there is a there's a problem here, you remove the value from NSW which was causing a problem. And now that you removed a problem, you're supposed to do constraint propagation, which involves rechecking the consistency of the following arcs, which is of the format some variable arc NSW, because NSW lost a value. This is just one instance of AC2 algorithm. This is how the condition is checked. The algorithm, I'll give an example. For now, I shall end the meeting. Looks like nothing much was covered. It's just simple minor one probably. AC3 I shall give you, there's a video that I found, so I will share the link to that as well. I'll have to check if it is the AC3 that we've been discussing in class, because it looked like AC2 to me. I'll share the video nonetheless. This class seemed light. There is nothing much important probably apart from AC2. Tomorrow I'll finish all the remaining topics. Hopefully I can probably give examples, or instead of giving examples, maybe just solve the minor paper and upload it. That would be better, I think. I'll try doing that. Fine. I will end the meeting now, and I will continue updating this notes and I'll upload it. Fine. I'll stop streaming.